So this leads to the Harris corner detector, which is Harris said, okay, instead of using sum of square differences, like Moravec was doing, there's a paper by Harris and Stephens, and they proposed a method in which they started using derivatives. So essentially, instead of using these values here, which is, remember, x plus delta x and y plus delta y, now they are going to take, they're going to compute this, taking a Taylor expansion, and you get an expression like this one, okay, to the first order. So you use and this is, again, delta x and delta y. So we can rewrite this function. I'm not going to follow, to give you all the derivation, but the idea is that if we rewrite this function, what we had before, essentially what we end up having is this M matrix here, which is a 2 by 2 matrix, where I have delta x and delta y here, and delta x and delta y here, and which is just the result of this operation. And remember the nomenclature we were using. Now, Ix is the derivative with respect to x, and Iy is the derivative, the partial derivative of the image with respect to y. Okay, so this means that in this M matrix, what we have is the derivative, the partial derivatives in the x and in the y direction, organized in a given way. Okay, we're going to see this in a minute. So essentially, this is the function that Harris detector is using, and what is taken into account is what's the intensity of my patch, what's the intensity of my patch at delta x and delta y, so shift in the patch, and we have this weight. This is wrong. It says window. It should be weight. It's a weight function. So this is weighting this difference. Why is it weighting it? Because sometimes I want to take into account the pixels that are closer to the center of the window are more important for me than the ones that are farther away. So I don't want to just give them all the values. If this weight is 0, 1, then I get a window. Then it could be a window function. Okay, but normally this is just, so this is what he's saying is that the pixels that are in the center have more weight than the pixels that are farther away. Okay? And then at the end, what happens is that I could do this bilinear approximation, and this means that M gets into this form. And M is this 2 by 2 matrix that I can compute from the derivatives of my image. And the first element is the derivative in the x direction to the square. So I do the square of the derivative in the x direction. And this is the derivative of my image in the y direction. And then I have the cross derivatives xy in the off-diagonal, in the off-diagonal components of this matrix. Okay? This is, in the case of the paper of Harris and Stephens, is called the autocorrelation matrix, this M matrix. And the idea is that you compute this M matrix for every pixel in your image. So for a given pixel, if I want to know if this is a corner, what I need to do is to build this matrix for that pixel. Imagine that I'm looking at pixel located at position 32, 109. Okay, so I go to my image, and I go x32, y109, and I open a window here and compute ix and iy. And once I compute ix and iy, what I'm going to do is to build this matrix here. And this matrix is encoding whether this pixel is a corner or it's not. Now let's see how this is encoding this. Normally, when I compute ix to the square and iy to the square for a given pixel, remember that here I'm at position 32, 109. Okay, so this is M for that pixel, and I have an M matrix for every pixel. This, looking at an eigen analysis of this matrix, I could know. Sorry, I take it back. I'll talk about eigenanalysis later on. But the idea is that M can be used to know if this is a corner or not, independently of the displacement that I apply. And if I'm in an homogeneous region, this M matrix is going to be very boring, and it's not going to be full rank. So it's going to be rank 0. If I'm in an edge, it's going to be rank 1. And if I'm in a corner, it's going to be rank 2. Okay? There are several corner detectors that are using this idea of looking at the partial derivatives and building this autocorrelation matrix or second moment matrix. And normally, no one is just looking at the rank. What people are doing is doing an eigen analysis. Okay, so I compute this matrix and I compute the eigenvalues of this matrix. If the two eigenvalues are big, as you see here, if here I have lambda 1 is the first eigenvalue and lambda 2 is the second eigenvalue of this M matrix. Now, remember, this is a matrix that I compute from the derivatives for every pixel in my image. So this is going to tell me, okay, this pixel, is it a corner? I look at the eigenvalues and I say, well, you know, if lambda 2 and lambda 1 both are small, I'm in a flat region. This means it's, you know, in that example that I put before, this is going to be like this pixel here. If one of them, if imagine that lambda 1 is big, but lambda 2 is small, I'm in this area here. This means that I'm in an edge. So it will be in this point here. And if both of them are big enough, this means that I'm in a corner. Okay? So the Harris method is just building this M matrix for every pixel and then telling us, okay, if I detect, if I compute the two eigenvalues and both of them are big, then this means that this is a corner. However, at the time that Harris and Stephens proposed their method, computing the eigenvalues was a very time-consuming operation because computers were not very fast and you had to solve a square root and you need to do it for every pixel. So again, imagine I have an image of 1000 by 1000, I need to do this 1 million times. Okay, and this was very time consuming. And then they suggested to use a measurement that they call R. And R is just taking into account what's the determinant of M and the trace of M. Remember, the trace is the sum of the main diagonal components of, so in this case, the two elements in the diagonal. So, and their R measurement was the determinant of M minus some constant that was set empirically to have a value between 0.04 and 0.06, and this was empirical, so just you set this value and everything runs more or less fine, times the trace to the square. Okay, and this is essentially an approximation of using the eigenvalue method. So it's the eigenvalue, computing the eigenvalues is very time consuming, so we're going to just apply this approximation. All right? The question is the rank of the matrix guaranteeing that I'm in a corner? So normally it goes the other way around. So normally, even if you are in a corner, you don't get rank 2 because of noise and approximation and quantization errors. So that's the main problem. Any other question? Okay, so let's look at the same thing we were doing with the eigenvalues, but now looking at R. So essentially, this is the same picture. What this is saying is you can also know if I'm in a corner or not, but just looking at the values of R. Essentially, if I'm in an edge, R is smaller in both cases, and R is bigger if I'm in a corner. Okay, this will be the separation. So essentially what you do is, since R depends on the eigenvalues of M, we're just going to compute R with the trace and the determinant and this empirical constant, and then I'm going to just retain the points that have an R value that is big enough. And then I'm going to decide for every pixel if it's above my threshold, I'm going to consider that it's a corner. If it's below the threshold, I'm going to consider that it is not a corner. Okay?